Hi, and welcome to the third episode of our isometric game series. Last time we created this map that is not flat anymore but has some elevation. And today I want to look into rotating the map viewpoint in such a way that we can, for instance, see behind these tiles that are obscured by this small hill here. So because this is a sort of 3D view, it's very nice if you can rotate the view so you can look at what's behind other things, stuff that might be occluded and be important to look into. So that's the objective for today. Rotating in an isometric world in such a cell-based grid-like environment. Let's look into a bit on how we can do that. So we have an isometric map and we want to go around. Now, when we talk about rotation, I'm going to create two constraints from the get-go. So the first constraint is that we only rotate around the z-axis. So we don't, that would be yaw in roll page yaw, I think. And we only rotate in 90-degree steps. So this means that in effect we can enumerate the 4 directions that we need to think about. So we have 4 directions and we will name them that describe the 4 rotations that we can have, because after 4 rotations, after 4 90-degree rotations, we're back where we started. And I give these the numbers 45, 135, 225 and 315 because that's the amount that the sprites that will render later on use to get the correct orientations. So that makes it easier to translate between the 3D world where we can render our sprites and the 2D SpriteKit world where we put them on the screen. So that's why we use these numbers and these names. So what does rotating around the z-axis mean? Well, because we only do a z-axis and we only do the there's a typo here, this should be a y. Because we do that and we only do 90-degree rotations, rotations will be quite simple. But first let's define the not rotated case. I define the 45-degree orientation as the default rotation, meaning there's no rotation. Also meaning that if I get an xy coordinate in, I will get the same xy coordinate out. When I do a 90-degree rotation counterclockwise, I'll end up in the 135-degree rotation, and that means that we need to swap the x and y coordinates and inverse the y coordinate. So this rotation is just playing around with the sign of the input coordinates, and also it's only swapping coordinates. And we do more or less the same for the other rotations. Only the transformation that we use to get from the input coordinate towards the rotated coordinate changes. And this is the final case. And after that you're back where you started. So let's start. I think we are ready to start getting this into code. So as a quick cheat sheet, these are the transformations based on the coordinates that we need to make. So let's get started. So let's jump into Xcode and let's start by creating some tests. So let's create a new marker. We will call this one rotation, and we'll create the first test. We will have a function called rotate coordinate, that returns an input coordinate for the default rotation, meaning it doesn't change anything. So let's get some input coordinates. For instance, let's see, so we have a -1, 1 and 0. And let's get a few more. -3, perhaps a 3, 1 and a 3, a z of 2 and -2. It doesn't really matter what you choose. Then for each coordinate in the input coordinates, we can assert that the rotate coordinate function that we still need to find, that takes coordinate and the direction, returns the same coordinates. Now we haven't defined rotation yet either, so let's first make sure that this can compile, meaning that we need at least the rotation and the new function. So let's go into our ISO converter and define rotation. So let's go up from the vector and let's create an enum of rotation. And let's see, we have a case degrees 45. We can't write something unfortunately like 225 degrees because Swift doesn't accept identifiers starting with a number. It assumes then that you are starting to create an integer with 2 to 5, and we have the case degrees 315. And we will have a default value. This returns rotation, and this will be the 45 degrees. If you choose another one as your default, that's fine as well. Then you just choose, for instance, this one. But as we said earlier, we defined the 45 as a default rotation. So if I go back to my test, at least the second part should work a bit better, but we still need to define our function. So let's go in the bottom and create a new function, and we will call this one rotate coordinate. And this one takes in a coordinate and the direction. And this one returns a new vector, so the rotated vector. And for now, let's just return a 0 vector. This should at least make the test compile. And now it compiles, we can run it for the first time and see it fail. And it fails because we are returning a hard-coded 0 value, while we would expect the similar components back. So let's make sure our test passes by simply returning the coordinate we already have. And now the test fails. But of course, this isn't yet what we want, because we want a true rotation, and this only works correctly for the if the rotation is a default rotation. So let's create another test that returns expected coordinates for a clockwise rotation. And let's get some input coordinates. Like 5, 2, 0. Let's get a few more. -1, -3, 4, 3, -7, -2. And let's also get some expected coordinates. something like 2, 3, -7 and -2, -5, 1, 3, -4, and let's see, for I in 0 for input coordinates dot count. Let's go over all one and assert that if we do rotate coordinates for the input coordinates I for the rotated direction, and I'll get back to direction in a bit, we will get back the expected coordinates I. The direction, what I would like to do is do something like default rotation and then get a rotated 90 degrees counterclockwise property, but that one doesn't exist yet, so that one we should definitely define in our rotation. So let's go back to the rotation, and let's say we have a far rotated 90 degrees counterclockwise. Did we do counter or did we do, this is for clockwise, so then we should make sure we do this only for a clockwise rotation. So we do clockwise. This will return a rotation, and so the way we can get a clockwise rotation if we can go, for instance, from 135 to 315. The way we can do a rotation, a clockwise rotation, would be, for instance, if we are at degrees 45 and we rotate 90 degrees clockwise, then we would end up in the 315. So we want to move through these enum cases, and probably the easiest way to do so is to make sure that the rotation has a raw value, and we can use the actual rotations here, and then what we can do is we can say our current rotation in degrees is our self.raw value. Then we can say our rotated degrees is degrees plus 360 minus 90, and the reason why we add 360 is that if we then do the modulus for 360, we never end up with negative values. And then we can do rotation for a raw value of rotated degrees, and this should always work. So now we have a property that returns the current rotation rotated by 90 degrees. So let's get back to our test, and this one should now no longer, the compiler should now no longer fail, so we should be able to run the test. And the test fails because we're not yet rotating. So let's go back to our converter and start implementing it properly. So let's see. So this is actually kind of easy, because what we can do, we can use a switch on the direction, take every case, and then decide what to do. So for 45 degrees, that's the default one, we can just return the current coordinates. If it's 225, that's mirrored in the origin, then we can return a new vector that has minus the coordinate of the x and minus the coordinate y. This is basically this case. And the C value doesn't change. And the other ones are really quite similar. So we have the 350 degrees. That is this one. So we have y minus x. So we do y minus x. And this needs the Z property. And the final one is 135. That takes, let's see, (135) minus y, and then the positive, and then. So if we run the test again, it should still fail. It should run now, but let's have a look to see if this, if we made a mistake. So we're doing clockwise rotation, and we are negating not completely in the correct way. So let's have a look. If our expected coordinates are actually correct. And I think the problem was the input coordinates. So let's test again. Okay, cool. So if you use a cheat sheet for something like these expected coordinates, of course you need to make sure that you copy them correctly. So this is clockwise rotation. We can do something similar for counterclockwise rotation. So let's do that as well. I think we can use what we can do is use the input coordinates as the expected coordinates. And the other way around. This saves some time copying over values. And then we need to make sure that we rotate it 90 degrees counterclockwise. So this one doesn't exist yet, but so let's copy this one and make one that is rotated 90 degrees counterclockwise. And in this case, because we're always adding 90 degrees, we don't need to do the plus 360. This should now compile. Oh. And this test should also pass. Okay, so we are now able to rotate around correctly. So I want to do one final test, and that is to make sure that C values don't change, because while rotating around the Z-axis, the C values should stay the same. So let's do a rotate coordinates does not change Z property. We have our input coordinates. We can use these ones, but we can add some Z values. And then we can go over each one of them and assert that rotated coordinate for C is the same as the input coordinate.c. Okay. So we're now able to rotate coordinates. What we now should do is make sure that our convert world to screen position takes the rotation into account. So let's write a test for that. So write a test that we convert a world to screen takes rotation into account. And we'll have a couple of rotations, an array of rotations, and this will be 45 degrees, 135, 225 and 315. Then we'll create a couple of test cases. We'll create a random coordinate. Let's quickly create a property that creates random vectors. So this can be something like this. Then we have a converted coordinate. And this one should take a direction into account. Then we have a rotated coordinate. That's how we use our rotate coordinate function. Take in the coordinate and the rotation. And we have an expected coordinate that is convert world to screen that takes in the rotated coordinates. And then we assert that the converted coordinate is the same as the expected coordinate. So basically what we're doing for the second one is that first we need to go through all the rotations. But what we do is we manually rotate the coordinate and then convert it to screen space. And what we want to check is that if we have a converted coordinate from convert world to screen that already has rotation into place passed in, that they return the same value. So let's make sure that convert world to screen also can accept the direction. Let's go back. Let's make sure we have direction here, and this one can have a default value of a default rotation. So this one should now compile, and now if we run the test, you will see it fail because we're not taking the rotation into account yet. So what we should do in this function is we first we take a rotated world space position, that's rotate coordinate for world space position and the direction. And then instead of the world space position, we use the rotated world space position. So let's run the test and see if this helps. Okay, so now our convert world to space can take rotations into account, and it seems to return the correct value. So let's see if we can start using this in our game. So let's go to our content view and let's make our view a bit more complex. We'll use a Z stack that takes the sprite view on the back and then takes a V stack that starts with a spacer and then an H stack that takes in two buttons. One is rotate counterclockwise, and the other one is rotate clockwise. So let's see if this at least builds and runs. So we now have two buttons, but they don't do anything yet because there's nothing, we're only printing out a statement. So let's make sure we can rotate the scene. So let's go to our game scene, and in our game scene we need to keep track of the current rotation. So I'll create a variable, initialize it as the default rotation, and I'll create a new function called rotate clockwise. This one changes the rotation, and we do something similar for counterclockwise. However, this doesn't do anything yet because we're only changing this variable and we're not redrawing anything. So what I want to do is I want to create a new function called redraw, and I'll call this function after updating the rotation. And the redraw function should take all this drawing stuff. So we can also call it here. Now, if we do this, then we will keep adding more and more sprites to the screen, overwriting more or less the other ones. So what I want to do is we need to make sure we clean up the old tiles we're showing first. And to do that, I need a root node. So this can be a simple SK node. We can add it to our scene. And then in the redraw function, I can clean up all the old nodes. So we can do for node in root node dot children node remove from parent, and this cleans them up. And now I can go into our content view and I want to write something like scene.rotate clockwise or counterclockwise. This means that the scene we now initialize here, we need to initialize on a higher level. So we can do it here. And then we can say scene.rotate counterclockwise and scene.rotate clockwise. So let's see if this builds and runs. So we have a view, let's rotate it. And we can't see any difference because we're not yet passing in the rotation. So here we're converting to a screen position. We need to pass in a direction and we'll pass in rotation. So let's try this again. So let's rotate and it seems something is working but not everything. And the reason is we're not adding to the root node yet. So the cleanup doesn't work. So let's give that a second try. So now at least no more new tiles get added, but what we see is, well, it doesn't really look good. So something is happening. However, the ordering of sprites is incorrect, and the reason for that is that our calculation of Z values, as in screen space depth, are not yet updated or taking the rotated coordinates into account. So we should make sure those are also taken into account, and let's create a test to do so. So we have a convert world to Z position function, and we want to make sure that it takes rotation into account. So we can do something similar as the one above, only this time we are interested in the convert world to Z coordinate, and this one will take rotation into account in a bit. Then we do the same thing convert to Z position, that's what it was called, and then we make sure that it's the same as doing it manually without any rotation past it. So let's go to our convert world to Z position. This one should take a direction, and it will have a default rotation, and this should now make sure that at least the test can be the test build. And now we should also make sure that it's used. So let's make sure that we pass in the direction here to the convert world to screen. So let's see if now the test succeeds, and if we now build and run, we should make sure to also pass in the rotation when we retrieve the world to Z position. Okay, let's rotate. So at least this now looks like it makes some sense. Finally, what I don't like is that when we rotate, we also move the map around, and the reason for that is 0, 0 is here, and we're more or less rotating around that point, but it doesn't look as good. It doesn't look like true rotation yet. And to solve this, what I want to do is I want to move the camera to the new middle point of the map. So basically the camera looks like that it stays in the same place. To do that, we need to move the camera around, meaning that we need the camera outside of this function, so we have a reference to it elsewhere as well. So we'll have an SK camera node, meaning we don't have to create a new one here. And in our redraw function, we move the camera, and we do that by saying we have a camera screen position, that's where we convert a world point to a screen point for the middle point of our map. So that's 2, 2, and the direction will be our rotation. Then we say camera node or position equals our camera screen point dot x and our camera screen position dot y. And if we now build and run, if we rotate, it really looks like we're rotating our map around. Can get rid of these print statements now. And this is all for now. This is enough to do at least the basics of rotating the camera. Next time I want to start with adding sprites to the scene, that represent units on the battlefield. Things we can move around, but first we'll make sure that we can show them on the screen, that they have the correct orientation also when rotating around, and should be interesting. So thanks for watching and have a good day.